Hey guys, how's it going? We're going to use this PowerPoint from Pearson from your book today, and we're just going to look through a couple things before we get started on some problems. So you've already read, hopefully, so you knew what the objectives were going to be. Find reflection images of figures and identify line symmetry. So you might have remembered some of these pictures here, and now we're just going to make a little more sense out of it. What we can see here is that when we flip across a line of reflection, right, the pre-image and its image are congruent and have opposite orientations. So as we read the vertices triangle bug, I love that, triangle bug, is clockwise, then its reflection will be counterclockwise. And that's an essential piece to keep in mind, okay? We know that it's a rigid transformation because the size and shape are going to stay the same. That's one of the rigid transformations and isometries that we've been talking about. So a reflection across a line, take for example this point here, what we have is a reflection across a line R called the line of reflection is a transformation with these two properties. Okay, let's look at them. If A is on R, so here's line R and here's point A, it's clear to see that A is going to be reflected onto itself. It's just going to kind of rotate like that, if you will, but it's reflecting. Okay, we'll talk about rotations later. If B is not on R, so some point that's like way out here, in space, some kind of thing like that, okay? In this case, we have B, then it's going to be some units away from the line of reflection, let's say like 5 units to make it easy. Then we count the other side as 5 units as well. That's how we get the congruent hashtag marks, right? The congruent symbols. So what we're looking for is always a perpendicular bisector. Remember, makes 90 degree, where the point, like if I drew a point here and called that D, then BD, right, the segment BD would have to be congruent to the segment B prime D, right? That's what we're trying to get at here. And that's what this is saying here, all right? So hopefully this is not going too quickly, but quickly enough so that we get the understanding of how to do some of the problem sets here. So reflecting a point across a line, it says if we have a point P at 3, 4, and it's reflected across the line y equals 1. Now, y equals 1 is a special type of line. Do you guys remember what type of line? That's right, horizontal, right? And x equals a constant would be a vertical, and you won't see the exact difference here, but maybe you'll be able to think about the differences when you see the example out. What are the coordinates of its reflection? And solution says that we're going to have to draw it out, right? Like I said, always, when in doubt, draw it out. So you're going to graph point P, and you're going to graph the line y equals 1. That's a horizontal line at y equals 1. Point P and its reflection image across the line are equidistant from the line. Okay. So we take a look at this next image here, and you can clearly see that we are so many units away from the line of reflection from point P. Now you can clearly see, I hope, that we're going down 1, 2, 3, so that's 3 units down. Now I should really write negative, but for distance sake, we're just going to use the positives, which means that the other one, to get to P prime from the line of reflection, must also be 3 units. Okay? So it's an equidistant, right, from the line of reflection. And if you notice here, the point is very easy to read for P prime. It's going to be what? 3, comma, negative 2, right? Easy to see, right? Has to be. You guys okay? All right. Move on. So very straightforward. Like I said, if I drew something that was vertical like this, and I had a point here, and it reflected around this line of reflection, then the point would end up over here, right? 1 unit away. So you're just looking at a basic count, and you'll notice what changes. In one, like the horizontal line, you'll notice that the inputs or the x don't change. However, you'll notice that in a vertical one, when x is equal some number like x equals like -2, for example, that we have here, that what does change? Is it the x? Is it the y? Which is it that changes here? Which is it the one that doesn't change? How about I say that? Which value doesn't change? Yeah, y. So you can start to see the relationship between the vertical and the horizontals. So, graphing a reflection on an image. Well, this is now easy as long as we know where the line of reflection is. And in this case, I'm just going to make a highlight to show you what the line of reflection is here. Okay, that's the y-axis. So we're going to make the line of reflection and it's shown in red. I'm highlighting it to show you a little better. I'm now going to use the color system here, and I'm going to count how many places I am away from point A, to the line of reflection. Well, that's 3 units. So if I want to be a perpendicular bisector and have this equidistant, then I must also go 1, 2, 3 units to the right, and that would be A prime. The same thing can be said about C. That'd be 1, 2, 3, 4, technically in the negative direction. So I would move 1, 2, 3, 4 there. And that would be C prime. Okay? And B, of course, is going to equal itself because it's right on the line of symmetry. So when we put it all together, it should look something to the effect of bloop, bloop, and bloop. Okay? So let's take a look and see what we have. So as we said, the step 2 is to find the image, right? So A prime, B prime, and C prime indicate the image. And you can see what they did here. B prime is the same position, like we said. And we have to locate A and C prime so that the y-axis is a perpendicular bisector. And if you look at ours and theirs, it looks very similar, as you can see here. Theirs is in blue, A prime, B prime, C prime. And notice the different orientations. A, B, and C are in a counterclockwise, while A prime, B prime, C prime are in clockwise rotation. Oh boy, the word problem! You get to hear me read. Yay! Okay, so minimizing a distance. Beginning from a single point on the summit trail. So we're somewhere on the summit trail. We're moving on the summit trail. We're moving on the summit trail. We're moving. We don't know where we are, but we're somewhere on the summit trail. So we're going to call this the line of reflection. Okay? And by doing so, you'll be able to see how to make the shortest point possible here to do the problem out well. Now, let's go through the problem. Okay. So if we're looking at this and we know that we have to do some reflections, we could do it one of two ways. Let's look at it the way that they have done it here. Okay. Is everybody okay with this so far? Should I read more? You want me to read more? Yeah, okay. Let me read the whole thing. Beginning from a single point on a summit trail at a hiking club, we'll build 2 trails, one trail to the overlook and one trail to the balance rock. Working under a tight budget, the club members want to minimize the total length of the two trails. How can we find the point on the summit trail where the two trails should start? Assume the trails will be straight and that they will cover the same terrain. Dun dun dun. Well, it's kind of hard to actually cover the same terrain if we use R to O here, because we're going to go across this rock. So it kind of makes a little more sense to see about moving O, and that's exactly what we're going to do. We're going to reflect O about the summit trail. And when we look at that, we can see the solution. We're going to do what? Move over here so much, whatever the distance is, we're not really sure, but we're going to take that same distance and we're going to create a point called O prime. Now, why are we doing this? Hopefully you'll see in a moment. Now we're going to connect the two points R and O prime. Now, when we do so, notice what it's going to intersect. It's going to intersect that summit trail. And that's an important part. So let me make a purple dot right here. Okay? Now that we have that part, right? Because that's going to be the shortest distance, and I'll call that, for what did they say? They call it point P. Okay? So I'll call it point P. I'm not drawing line T in here just because I want to make it look a little bit nicer, and you'll see the whole picture drawn out in a moment anyway. But now what we can say is that we know that a line is the shortest distance. So R to P is the shortest distance, and therefore if I'm on the trail, P to O prime is going to be the shortest distance to go to get to that place. Well, if we connect P to O right here, correct? Then we also notice that these two are actually going to be what? Congruent, making an isosceles triangle. Therefore, we have shown that the shortest distance is going to be what? That's right. PO to get to what? Overlook. And RO prime to get to the other one. Or sorry, P to R to get to the other one. So the shortest distance between the 2 points is a line R, a segment actually in this case, R O prime is the shortest distance between R and O prime. Also, PO equals the distance of what? PO prime. So those two distances are the same. That's why they're congruent. If we start the two trails at point P, the two trails PO segment and PR segment will have a minimum distance. And that's what we were trying to get at with this image up here when we were working on it. Okay, now we're getting to the part that I was wanting to get to, the line of symmetry. Okay, so the line of symmetry is basically anything that has a reflection, okay, onto itself. If we read this really quickly, a plane figure has a line of symmetry or reflectional symmetry if the figure on the side of the line is a reflection of the figure on the other side of the line. The line of reflection is called a line of symmetry. It divides the plane figure into congruent halves. So, like, in other words, distance equals distance, and that's the key. D1, D2, and they are equal. Okay? So, let's go into a little more depth here. So it says, how many sides of symmetry does a regular hexagon have? Well, I mean, it kind of sucks that it says solution, sketch it, and then study our figure for ways it will reflect across the line. Well, this is nice. It's a regular polygon, and hopefully you remember what regular means. It means that all the internal angles are what? Congruent, right? So we know this, and this are all the same angle, right? So we can bisect them, and then we know we're flipping on everything, every which way, right? So if I start up here, let me make it a little bit better because that's just not good. So if I make a segment here and try to do my best I can to make it look pretty good and then kind of continue it out here, then you can see that this yellow that I'm highlighting now will reflect onto the blue here. So we just have to keep going around and around and around until we actually find all of them. So here's one, another one, right? So we're just going vertex to vertex or vertex to vertex, right? So let's do this one in purple. Oh, that one wasn't a really good one. But I'm hoping you see the actual point here. So if we look at this now and we start going rotationally, and this time I'm gonna just look at it rotationally and counterclockwise. I'm gonna count this one as 1, 2, 3, 4, 5, and 6. Then how many ways are there to reflect across a line for this specific figure? 6. So here we have the hexagon worked out, and it says a regular hexagon has 6 lines of symmetry. And that will do it for us now. I hope you had fun. And now let's get into some problems and working some out on the lab. All right. Hope this helped. Have a good day.